Hey guys, Jake here, coming at you with another math lesson today. Sorry, I'm not doing it live this week. Bit of a scheduling issue on my part, so sorry about that. But wanted to come out with this video. Figured it was better a little later in the week than not being able to do one for you. I'm gonna go ahead and kind of keep the same live stream format that I normally do for these videos each week. So I'm going to be going through a problem here with you. It is a multi-part problem, bit of a long process, but I wanted to show you this problem because I think it's a good one to see because it shows you a lot of different things that kind of come along with calculus. A lot of the topics that we're going to be covering in this video are covered on my Calculus 1 study guide, which you can get for free if you just hop over to jakesmathlessons.com. There's a link directly to that page down in the description if you want to check that out as well. It's also covered in my complete Calculus 1 package. Both those things should be a huge help to you, so I definitely recommend checking out those links down in the description. But let's go ahead and jump into the video here. I know this isn't live, but if you do have any questions along the way, like I normally do with my live streams, feel free to throw them in the comments, and I'll be sure to check back and do my best to answer whatever questions you have. If I can't answer it in a comment, maybe I'll make a video about whatever question you do have. So feel free to do that. Let's go ahead and jump into the problem here. And I'll show you how to do this one. So basically we have this function here, f of x equals 2 plus 3x minus x cubed. And there's going to be several parts that we're going to want to do here. So first thing that we're going to want to do, or first thing that it asks us to do, I should say, is to find the intervals of increase or decrease, which essentially just means find what intervals your function is increasing and which intervals it's decreasing. Also, we're going to find the local maximum and minimum values. Those two parts of this problem are going to go kind of hand in hand. I'll talk a bit more about what I mean by that in a minute. And then part C is to then find the intervals of concavity and inflection points. So we're going to need to find where it's concave up and concave down, as well as finding our inflection points. And then we're going to use all this information from parts A through C to actually sketch a graph of this function. So let's kind of break this down piece by piece. Really, when you're doing any sort of problem like this, and like I said, this is a pretty common problem that you're going to run into where they ask you to find all this information and use it to sketch a graph of your function. Whenever you're doing these problems, you can see that, part A and B, they ask us about where our function is increasing or decreasing. They also ask us for local maximum and local minimum values. And then in part C, they ask us for intervals of concavity and inflection points. All of these pieces of information can be gathered from our function's derivative and second derivative. So really the first place you want to start when you're doing any of these problems is to start by taking the derivative of your function. So the derivative of this function can be found just by using the power rule. The power rule just says that, well, the derivative of a constant is just 0. The derivative of 3x is just going to be 3. And then the derivative of minus x cubed, we're going to bring the 3 down in front, bring the power down in front, and then subtract 1 from our power. So 3 minus 1 is 2. And then you're just going to leave your x as x. Okay, so there's our first derivative. Then, like I said, we're also going to need to use the second derivative. So we can go ahead and find the second derivative of our function. To find the second derivative of any function in general, all you have to do is just find the derivative of the first derivative. So the derivative of a constant 3 is 0. And then minus 3x squared can just be found with the power rule again. We're going to bring the 2 down in front, multiply it by the negative 3. So that gives us negative 6. And then leave the x as x, and then minus 1 from the power. 2 minus 1 is 1. X raised up to the first power is just x. So our second derivative is just going to be negative 6x. Okay, so now once we have our first and second derivative, there's going to be a kind of a few steps that we want to think about. So let's go ahead and start with finding our intervals of increasing and decreasing. That's generally going to be the easiest thing to start with, but both part A and B, where we're trying to find our intervals of increasing or decreasing, and find where we have local maximum and minimum values, those are both going to require us to find our critical numbers. So how do you find the critical number of a function? Well, all you have to do is take the derivative and set it equal to 0 and solve for x. So we already have our derivative. It's 3 minus 3x squared. So we're going to take 3 minus 3x squared, and we're going to set it equal to 0. And then the other thing we want to keep in mind in general when you're trying to find critical numbers, you would also need to figure out where does your derivative of your function not exist? Where does f prime does not exist? Which x values would cause that? Well, in this case, f prime is a polynomial. Polynomials exist for all x values. F prime, and f double prime are all polynomials, so we know that all three of these functions are going to exist for all x values. So this actually is not going to come into play here for our critical numbers. So we really just need to worry about where does our derivative equal 0. So to solve this, we can subtract 3 over to the other side. Divide both sides by -3. And that gives us 1 equals x squared. Take the square root of both sides, and do be careful when you take the square root of both sides in an equation like this, you want to take the positive and negative square root. So we're going to get x equals the square root of 1 is 1, so we're going to get plus or minus 1. So we have two critical numbers, x equals 1, x equals -1. So now what we want to do to figure out where we have intervals of increasing and decreasing, we want to take these two critical numbers that we found and put them on a number line. So we're just going to start with a number line. And we're just going to draw our critical numbers on there. So -1 and +1. Okay. A common mistake I see people make with this sort of a problem is they will always put 0 on here. You don't want to always put 0 on your number line. You only put 0 on the number line if 0 is a critical number. In this case, it's not. So we do not want 0 on there. We only want to put our critical numbers on there. Once you do that, what you can do, and this is basically to use the first derivative test at this point, splitting your number line by the critical numbers is going to create different intervals. So you can see if you imagine this number line of all real numbers from -infinity to +infinity, we split it at x equals -1 and x equals 1. So basically what we just did was we created 3 intervals, right? We created an interval here, we created an interval in between these two numbers, and we created an interval over here. So what I like to do is just kind of think about what are the intervals that you just split your number line into. Well, we split it from -infinity up to -1. We split it from -1 up to +1, and we split it from +1 to +infinity. So we basically just created these 3 intervals by splitting our number line at our 2 critical numbers. Notice the edges of all these intervals are round parentheses rather than square brackets, because we don't want to actually include our critical numbers within these intervals. The reason for that is the critical numbers tell you where the derivative of your function equals 0. What that means is that is the point where f of x, the original function f of x, has a slope of 0, right? Because the derivative of a function tells you about the original function's slope. So if the derivative is 0 at -1 and 1, then the slope of f is 0 at those points. If a slope is 0, that means our function is not increasing or decreasing. So we don't want to include our critical numbers within our intervals. Now what we want to do is pick some numbers within each of these 3 intervals. It doesn't really matter what number you pick. You can pick whatever number you want, but it just has to be with one number within each of these 3 intervals. So let's just say we take -2, 0, and 2, because 2 is within this interval, 0 is within this one, and 2 is within this one. Now, basically what we can do is we can take those 3 numbers that we just came up with within each interval and plug it into f prime. Because again, f prime is going to tell us about the slope of f. So if we take these 3 numbers and plug them into f prime, the number that we get out is going to tell us what the slope of f is at that point. So if we know the slope of f is a certain number, that will tell us whether it's increasing or decreasing. Now, it's important to keep in mind, we don't actually care what specific number we get out of this. We just care if it's positive or negative. So f prime is 3 minus 3x squared. Let me just copy that down here. 3 minus 3x squared. Okay, So if we take -2 and plug that into this function, we would get 3 minus 3 times -2 squared, which -2 squared is 4 times -3 would be -12. 3 minus 12 is going to be -9. And again, it doesn't really matter that we got -9. What's important is that we got a negative number. So what that tells us is if f prime is negative, that means the slope of f is negative. If the slope of f is negative, that means it's going in this downward direction. That tells us that f of x is decreasing throughout this interval. So basically we know that the interval of -infinity to -1 is a decreasing interval. It is an interval of decrease. So that answers part of part A. We do still have to figure out these other two intervals now. So again, we're going to do the same thing. We're going to plug now 0 into f prime. So that's going to be 3 minus 3 times 0 squared. 0 squared is 0 times -3 is 0. 3 minus 0 is 3. So this is positive, which means f has a positive slope, which means f is increasing from -1 to 1. Okay, and then we're going to do the same thing with +2. 2 squared is 4 times -3 is -12, which again gives us -9. Negative slope for f within this interval means that we have a interval of decrease right here. So what that tells us is we have 3 intervals of increase or decrease. We have an interval of increase from -1 to 1. F is increasing from -1 to 1. And we have an interval of decrease from -infinity to -1 and from 1 to infinity. So increasing from -1 to 1 and decrease from -infinity to -1. And this little u just means the union. So basically these two intervals are both going to be intervals of decrease, basically intervals where our function is decreasing from 1 to infinity. Okay, so that would be it for part A. Now part B is going to quickly and pretty easily build off of part A. And the reason for that is, let's think about the general kind of shape of our function at this point. We know it's decreasing from -infinity to -1. It turns around and starts increasing when we get to -1. And it continues increasing until we get up to x equals +1. And then at that point, it turns around and goes back to decreasing. So in general, the general shape of our function, basically, we're decreasing, increasing, decreasing, right? So you can basically see at x equals -1, we turn around and start increasing. At x equals +1, we turn around and start decreasing. So what that kind of shows us is, if we're thinking about now for part B, let me just go back up here real quick. Part B is to find the local maximum and minimum values of our function. If we know what intervals our function f of x is increasing and decreasing, that gives you a general idea of its shape, right? You can pretty easily look at that and see, okay, if we're decreasing to the left and increasing to the right, that tells us we have a local minimum value at x equals 1, or -1, I'm sorry. And then if we are increasing to the left of this point right here and decreasing to the right of it, increasing to the left, decreasing to the right, that tells us, you can see we have a local maximum, right? It's higher than all the other points around it. So basically the first derivative test tells us that. It tells us if we're decreasing to the left, increasing to the right, it's a minimum. If we are increasing to the left, decreasing to the right, it's a local maximum. If, for example, we were decreasing to both sides of a critical number or increasing on both sides of a critical number, like if we had something like this, where we had a critical number right here, we were increasing to the left and to the right, that would not be a local maximum or a local minimum. In this case, the first derivative test confirms that we have a minimum at x equals -1 and a maximum at x equals 1. So this would be our answer for part B. where our local maximum and minimum values are. Okay. Now moving on to part C here, we need to find the intervals of concavity and inflection points. So this is really not going to be too different from what we had to do for part A. Finding intervals of concavity is very similar to finding intervals of increasing or decreasing. Finding inflection points is very similar to finding critical numbers. Of course, part A didn't tell us to find critical numbers, but we had to find them in order to find the increasing and decreasing intervals. In order to find inflection points, we're going to need to do effectively the same stuff we had to do for this up here, except we're going to do it using the second derivative instead of the first derivative. So let's start by, let me just write down our second derivative down lower. So the second derivative of this function is f double prime equals negative 6x. Okay, so to find inflection points, if you already know the second derivative of your function, in order to find inflection points, it's very similar to finding critical numbers. You want to be careful of where your second derivative equals 0. So we're going to look for places where the second derivative of our function equals 0. You would also want to be careful of considering where your second derivative does not exist. In this case, like I said, our original function f of x, our first derivative f prime, and our second derivative f double prime, all three of these functions are polynomials, meaning that all three of them are going to exist for all x values. So as a result, we don't need to worry about where our second derivative does not exist, but we do need to worry about where does our second derivative equal 0. Okay, so to do that, what we would have to do is take our second derivative and set it equal to 0 and solve for x. In this case, it's going to be pretty straightforward. If we divide both sides by negative 6, we just get x equals 0 is our only inflection point. So that's part of part C right there. Our inflection point is x equals 0. Okay, so what that tells you is very similar to what our critical number told us up here. What it tells us is that if we take a number line from negative infinity to positive infinity, and in this case, we're using negative infinity to positive infinity because our original function f of x is defined for all x values. If we had a limited domain on this f of x, we wouldn't want to use all numbers. We would want to basically cross off whatever sections of our domain are not going to work. In other words, we only want to look at the x values that are a part of the domain of our original function f of x. In this case, that is going to be all real numbers. So our number line is going to be from negative infinity to positive infinity. And then the only point that we want to put on our number line is our inflection point. So now, very similar to what we had to do with increasing and decreasing, you can see that that basically split our number line from all real numbers into two different intervals here. Okay, so I like to, again, just write those intervals down. We have now from negative infinity up to 0, and from 0 up to positive infinity. And again, these intervals should not include your inflection point, because the inflection point is the place where your function does not have any concavity. It's switching from concave up to concave down potentially, but it doesn't, that one specific point, x equals 0, does not actually have any concavity to it. You can kind of think of it as like a tiny little piece of your function that's like going in an actual straight line. Concavity basically just means curvature. So this point where it switches from curving upward to curving downward, or vice versa, that one little point where it actually switches from one to the other does not have any curvature to it. So we don't want to include our inflection point within these intervals. Now what we want to do is we're going to take, again, some number within these intervals. Doesn't really matter what number you pick. Let's just say -1 and +1. And we want to plug those numbers into our second derivative. I'm sorry, our second derivative is here. So we're going to take -1 and +1 and plug them into f double prime. Okay. If this is making sense so far, do me a favor and drop a comment down below. Just say got it so far so I know you're following along. And if you are getting some value out of this video, go ahead and just hit that like button too while you're down there, please. Be a huge help to my channel so we can get this video out to more people and keep doing well in calculus all term. So we will take these two numbers that we selected within this interval and plug it into our second derivative. So that's going to give us -1 is going to give us -6 times -1. +1 is going to give us -6 times +1, which is going to give us +6 for x equals -1 and -6 for x equals +1. So again, just like in the last part where we were looking for increasing and decreasing, when we're looking at concavity and looking at what output we get from plugging in these numbers into the second derivative, we don't really care what the specific number is. What's important is whether it's positive or negative. Since our second derivative is positive within this interval, that tells us that our original function is concave up. It's like a smiley face, right? It's curving upward. Because similar to how the first derivative of a function tells you about the slope of the original function, the second derivative of a function tells you about the concavity or the curvature of the original function. So if we know the concavity is positive, that means it's curved upward. So that tells us that our original function has an upward curve to it. Here we got a negative number as an output for our second derivative. That tells us that our original function is curving downward. It's concave down. It's basically like a frowny face shape. Okay, so our original function is curving up over this entire interval, and it's curving down over this entire interval. Okay, so that tells us our intervals of concavity are going to be concave down from 0 to positive infinity, and it's going to be concave up from negative infinity to 0. So these are going to be our intervals of concavity, okay? And then our inflection point is just x equals 0. So that's going to be it for part C. So now part D is where we kind of put all this together. What does all this mean? We've figured out a few things here. We've figured out that our function is increasing and decreasing on certain intervals, which kind of give us a general idea of this sort of a shape of our function. We also confirmed that we have an inflection point at x equals 0, and that we are curving upward to the left of 0 and curving downward to the right of 0. So if we kind of put all that together, we actually see that this kind of original sketch I did here is really not too far off. Basically, we're going to be decreasing to the left of -1, increasing until we get up to 1, up to x equals 1, and then decreasing for all x's after that. And what we found out in part C here, it switches from curving up to curving down right at x equals 0. It's going to be curving up everywhere to the left of that. So it is going to be curving upward, off to negative infinity in this direction. At x equals 0, we're going to switch from curving upward to curving downward. So basically we're curving up until we get here, then we start curving down. We hit a maximum at x equals 1, and then we keep curving down and going down. So basically our function is decreasing and concave down all the way up to x equals positive infinity. So it is going to have this general shape. What we could do to get a little bit better sense of exactly how high up or down our function is actually plug in some points to actually get a value for our function. So let's just say we wanted to, it really doesn't matter which points you plug in. There's not a strict guideline on this of how good of an idea you need. There are some other things that we can kind of figure out in terms of how our function is behaving, especially if we want to look at like what x does going at, what our function does as x goes off to negative infinity or off to positive infinity. But what we could do if we wanted to is just plug in some x values. So we could plug in like x equals -1, x equals 0, x equals +1 back into our original function. just so that we can get some XY coordinates that we could put on our graph. I'll leave that up to you so you can get a little bit better idea on that. And if you wanted to take this a step further, just to get a little additional practice, what you could do then is find the limit as x goes to negative infinity of your function f of x. So 2 plus 3x minus x cubed. And also the limit as x goes to positive infinity also, because that can help kind of give you a sense if this does truly just go up to infinity forever and down to negative infinity forever, so that you can get a little bit better idea in that sense as well. So now what I wanted to do is just kind of confirm what this function actually looks like. So what I have here is just going over to Wolfram Alpha and showing you what the graph of this original function actually looks like. So you can see this does look, basically it does fit the kind of requirements, I guess you could say, of what we figured out, right? You can see we do have a local minimum right here at x equals -1. Let me see if I can zoom into this a little bit for you, actually. Okay, perfect. So you can see we do have we do have this local minimum here at x equals -1. Our function, you can see this first one here is a little bit more zoomed in. It only goes from -1.1 to 2.1. This version here is the same function, but zoomed out quite a bit more. Sorry, got a little tickle in my throat. But you can see we do have a local minimum here, right at x equals -1. Sorry about that. There is also a local max here at x equals +1, which is what we figured out. And it's a little harder to see this in the graph, but our math did confirm it. You can see right at x equals 0, right here, we actually switch from curving upward to starting to curve back down. So right at this point, it flips from curving upward, kind of that smiley face shape, to curving down into that frowny face shape. And then if you did take it a step further, like I suggested, and figure out the limit as x goes to -infinity and positive infinity, you would have seen that what we actually had of having, x, or our function go up to infinity as x goes to -infinity, and our function going down to -infinity as x goes to positive infinity would have been accurate. So you can see that our sketch, what we got from figuring out these inflection points and critical numbers and max and min and increasing, decreasing, concave up, concave down, all that stuff confirms exactly what using Wolfram Alpha or any other graphing software would have confirmed for you as well. So that should give you a pretty good idea of how to do those sorts of problems. If you did get some value out of this video, do me a favor and hit that like button down below. It'll be a huge help to my channel so I can keep making more videos like this. And hit that subscribe button down there with that bell icon as well, if you want to keep crushing it all term long in calculus with me. Like I said, feel free to drop any questions you have in the comments, and I'll do my best to answer those. But otherwise, thanks for joining, and hope to see you next time. Thanks.